So again, 0.5 centimeters must be above the water. If it's 2 centimeters thick and 1.5 is below, 2 minus 1.5 gives you a half. So at least we know how much of this is floating and how much of this is submerged. Now bless you, thickness. Okay, and thickness. Now, in these problems, we don't care about the thickness that's above the water or in the water. We care about the volume that's above or below the water level. So look at this bar of soap right here. If I'm looking at the bar of soap and I think about volume, can you tell me specifically, focus, come on, tell me specifically about how much of the volume of the soap is underwater compared to how much of it is above water? What would you say for volume here? There's more underwater for sure. Does everybody see that? There's more underwater? Can you give me a proportion or a fraction of how much you think of the volume is underwater? 3/4 of it. Again, some of this is just straight up intuition. But let me explain in case you're having trouble with this. Imagine that, let's see if I have a table that works. Oh, here, perfect. Here's the bar of soap. Okay? Now, the bar of soap, again, we said that about 1.5 centimeters underwater. So where my finger is touching is where the water level would be. Most of it is underwater, a little bit is above water. I'm not giving you anything about the width and the length. Yet we're somehow coming up with this idea that the volume is able to be calculated. But we're not actually calculating the volume itself. What we can say, though, and this is what George was just saying, is that the volume that's under the fluid is equal to 3/4 of the actual volume. Remember, these are capital V's here. Capital V's, not lowercase v for velocity. That was section 12.3 when we looked at velocity. So this is absolutely true. George just uses intuition to figure that out. There's not a number. You're not being told, you know what? The volume is 12. So 3/4 of 12, that'll give you 9. No, it's not what we're doing here. We don't have the actual volume at all. We're not given a number. All we're told is that 3/4 of the soap is underwater. So the volume that's in the fluid, the F, the volume of the object that's in the fluid, is 3/4 of the overall volume. Again, that's what this statement says here. The volume that's underneath the fluid level, or that's submerged in the fluid, or the volume of the fluid displaced, is 3/4 of the actual object. And where does the 3/4 come from? George, where do you get 3/4 from?
1.5
Yeah, the amount of water, the amount of the soap that's underwater is 1.5 inches or 1.5 centimeters, and it's got a total height of 2 centimeters. So 3/4 that reduces to.
I thought you just said if it was like 12 and it said it's not right.
Well, what I'm saying is this: we don't know anything about the actual volume. To calculate volume, you need the length, the height, and the width or depth. We're not given this or this. We're only given the height. But I know that a bar of soap is a rectangular solid. So if 3/4 of the height is submerged, 3/4 of the volume must also be submerged. Okay? But I don't know anything about the actual number yet. That's all I've got so far. Now I go ahead and I look at my object and I think about a free body diagram. It's floating. It's floating. It's floating. What state are we in? Equilibrium. Think about it for a second. If something is floating, literally, it must be balanced. If it weren't, what would happen to it in water or in fluid? It would sink. Okay, those are the two options. That's all we've got. So this whole chapter, this whole section about sinking and floating is about sinking and floating. That's it. If it sinks, the weight is more than buoyant force. If it floats, we're in equilibrium. So we know already that this must be in a state of equilibrium. So FB pulling up is the same as FG pushing down. Okay, that's got to be the case when it's floating. It's got to be. And if you didn't know this by now, go back to your 12.2 notes and look. We talked about when objects sink, what it means, and this is part of what it meant. So we know that there's equilibrium, so we can say the force acting up minus the force acting down equals 0. Again, what does it usually equal to? Newton's law, F equals ma. So this is really coming from this equation right here. Okay, but because, God bless you, because it's floating, there's no acceleration. Okay? Just so the clear, so where this comes from the sum of all the forces, meaning the buoyant force pushing up and the weight pulling down, equals ma, but a is 0. If it were more, it would be lifting it out of the water. Like, think about it this way. Normal force, right? Guys, this is a great question. Why isn't FB more than FG? It might be more than FG when you push it under the water, which causes it to do what? Shoot up to the top. But once it settles on the top, which it is right now, it's not being pushed up. It's not being pushed down. It's stationary. So remember how normal force, if the weight of this hand sanitizer is 1 Newton, and it's pushing down, what's the normal force pushing up? 1 Newton. Normal force can never exceed what's pushing down. Same thing with the buoyant force when it's at rest or when it's actually floating. But remember the beach ball example? You take a beach ball and you hold it under the water, let go. What happens? Shoots out of the water. That's because when you submerge it, you're making the buoyant force greater than the weight and causing a net force upward, which is causing it to rise up with acceleration upward, and it accelerates out of the water. Here, it's stationary equilibrium. Okay, good question. Very good question. Now, filling in our formulas here. Our formula for buoyancy is rho F VF G. That's given on your formula sheet if you don't have it memorized yet. It's the density of the fluid times the volume of the fluid displaced times gravity. What's the formula for FG? FG. mg. Why am I putting a little O there? What does this little O represent again? Object. And F stands for? Fluid. F is fluid, O is object. Now, you need to recall this information. What is the definition of density? Mass over volume. So I could technically solve for mass in this formula. We did this already in class. This should be kind of a review. Okay, this part right here. Solve this formula on the right for mass and plug in its expression for mass here.
You said that term is on.
So the buoyant force equaling this is on your formula sheet. It says FB equals rho F VF G.
Oh, yeah.
See it? Yeah. Now, this formula is also on your formula sheet right here, but you need to solve it for mass. And mass is simply density times volume. So I'm going to place density times volume right here in for mass. And then everything else carries down. Okay, take a look at what I've got. I've replaced mass with rho V because that's the definition of mass from this formula. This is something that we've done. This is the third time you're doing it now, where you're solving for mass over here, getting rho V, and replacing mass with rho V. So I know it's like, I've only seen it 3 times. Be accustomed to doing this. All of these problems, you're usually not given any information about the mass of the object itself. So you do everything in terms of its density and volume. Okay, now, the beginning part that George helped us with is going to come into play right now. So start with this first statement that we've got here, that VF is 3/4 of VO. If that's the case, what can I do with that statement at the top? At the top, it tells me VF is 3/4 of VO. What can I do with that? I want to use it somehow. How can I use it? How can I use it? Juliet, what do you think? Jimmy, you going on? So we could just pick numbers here as a result. Yes. What else could we do to make it even better? Yes, you're right. We could just use numbers.
I was going to say replace VF with 3/4 VO.
Yeah, use substitution method and just plug the whole expression in for VF. Remember, substitution tells us that if VF is equal to 3/4 VO, like up here, we can take that and plug it in right there for VF. Just like we replaced MO, the mass of the object, with density times volume from the formula over here on the far right, we can do the same thing. But Juliet, if you use numbers, that works too. Yeah, you could have chosen arbitrary numbers and it would work. So I've got the density of the fluid times, instead of VF, we're going to put 3/4 VO times G minus density of the object, VO times G. Again, it looks like a tricky problem because we've got a lot of stuff going on with variables and not much with numbers. But at this point in the year, you should feel somewhat, confident in your work with variables, not just numbers. Ernst? Okay. Now, notice everything equals 0, doesn't it? When you solve quadratics in your math class, if all of the coefficients were even, what did you start by doing? And it was set equal to 0. What did you always do? Divide by?
Well, you cancel out.
Yeah, so you divide everything by what if they're all even?
2.
2. Right? It could be itself possibly, but 2 most likely. So if I had something like 2x squared plus 6x minus 8, everything's divisible by 2, right? So wouldn't you just divide everything by 2 and get rid of it? Start? What do you notice here? Remember, forget the 0. What's in both of these terms? What's in both of them? Well, G. What else? Ernest? VO. So divide all three terms by GVO at this point. Now, 0 divided by anything is still 0. That's why this is useful. We're left with rho F times 3/4 minus rho O. Really convenient. I mean, it's literally so convenient to do this problem this way because of the fact that VO and G drop off. VO and G drop off. Move the density of the object over to the right side. So what do we know about the soap? The soap, here's how I would read this. Okay, I'll point so you guys can see. The soap has a density equal to 3/4 of the fluid. Again, the soap, this is how I would read this, has a density that is 3/4 of the fluid itself. The fluid's density was given as, is not given actually right now, but the density of water is just 1,000. Okay, but again, this is the key here. The density of the soap is 3/4 of the water. That means the density is less or more than water. If it's 3/4 of water, is it less or more than water?
Less.
It's less. And when things are less dense than water, what do? They float. Makes sense, right? The answer that it's less than the water itself. The water is 1,000, it's 3/4 of that, or 750. Keep it like half.
Yeah.
Okay.
So if for swimming, for drowning, does that mean that we were able to shift our density to make us be more against the water?
Absolutely. That's remember I gave the example in class. If you dive down to the bottom of the pool and blow all the air out of your lungs, you're decreasing the volume of your body, which increases your density. You'll stay on the bottom of the pool. But if you go down to the bottom, swim there, and don't hold on to anything, you eventually will start to float back up to the top because you have all that air contained in your body, which makes you have a lower density, so you want to float. But if you blow all that air out, you can literally sit at the bottom of the pool and kind of like just lay there on the actual bottom of the pool. It's kind of cool. And yeah, it's the same thing as like we talked about blowfish. Okay. All right, let's go to the next example. Okay. So if we're looking for a number, by the way, water was 1,000. So this is going to be 3/4 of 1,000. The density of water is 1,000. So this would be 750 for the soap. All right, example 2.
Is it like on the test, could there be questions that don't really numbers? Like for this, the answer is not this. Density of the fluid is 3/4.
You mean density of the object?
Density of the object is huge.
Sure. I would accept that as an answer because it's right. Okay? But I would give you the density of water and then you can just plug it in also. So you don't have to, but that would be definitely perfect. It's like solving algebraically, right? That's what I was talking about. Same thing. So an object weighs 315 newtons in air. What are we in right now, guys? We're in air, right? I talked about this yesterday with the other class. You are actually always submerged in fluid. But the fluid you're submerged in right now happens to be air. Are you more dense than air or less dense than air? You're more dense. Dense. You're more dense than air, meaning that you sink to the bottom of the air. Well, if you were less dense than air, what would you do? Like a hot air balloon floats, right? It's less dense than air. So right now, you are submerged in a fluid, that fluid being the air around you. Okay? So the current weight of an object in air is 315. That's its normal weight. When it's immersed in water, it only weighs 265 newtons. Why is there a differential right away? What's causing that differential in the weight? Once you're in the water, why do you weigh less? Because of what? The buoyant force. So could you tell me right away what the buoyant force is in this problem? What's the buoyant force going to be in this problem? Not 265.
Not 7.
Not 275. So forget the oil for a second, though, okay? I'm only on the first part.
Oh.
When immersed in water. 50. 50. Let's explain. Why 50? Mite?
The weight of the option outside there minus the weight of the option.
Yeah, however much you feel like you weigh outside, if you feel a little bit less weight in the water, the difference is the buoyant force. That's the buoyant force is causing you to feel like you weigh less. It's what's pushing you back up. Yes. Now, when it's put in oil, though, the object feels like it weighs 275 newtons. So we want to find the density of the object in the oil. Okay? So for a problem like this, we have to start thinking about our free body diagrams. So let's look at the first part. Let's look at part A. I know for part A, again, I've got something pushing up, something pulling down. I know that it's immersed in water. What does that mean, immersed? Immersed. Yeah, it's fully under the water. It's fully under the water. So is FG going to be stronger or is FB going to be stronger in this problem? FG. FG would mean if it's greater than FB, it would sink down. And that's what's happening right now. Come back to me, Nick. So it would sink back down. So the FG value is greater than the FB pushing up in this problem for part A. So we know that FB minus FG is equal to MA. Now, this object is at the bottom of the water, literally just sitting there. So there's no MA again in this problem. But the interesting part that we're going to recognize here is that the FB and FG value are not equal to each other. Okay, they're not equal to each other. So let's talk about this for a second. We know that the actual weight is 315. Let's write that down. That's right here. FB is not really known. We kind of know it, but it's not known, we'll say for now. Well, how much does this problem say we feel like we weigh when we're in water? What is it? What do we feel like? What is our apparent weight? Remember, the word apparent weight is what you feel like you weigh in water. That's going to go over here. Okay? So let's talk about this for a quick second. Normally, we would put MA over here for FNet. FNet equals MA. But in this kind of a problem, we're looking at a scenario where, you know what? There's a differential here, which is caused by this buoyant force. So if I were to take, in this case, the buoyant force and think about the gravitational force, what sign should I apply to this? What's the overall force acting? If I'm submerged and sunk, the overall force acting must be negative or down. Think about it for a second, guys. If you left that as positive, you get a huge number for FB. This negative here indicates that, yes, the overall force, that's the difference between these two, is negative. FG, this vector, is greater than FB pushing up. And this is where George got the number of 50. Simply take 315, add it over here. You'll get positive 315, negative 265. That will give you 50 for FB. It's not an answer, but it's a step along the way. So again, if I'm looking at these problems here, and I'm not given anything about the mass and acceleration, I might want to write FB minus FG equals MA, but I don't know what MA is. All I know is that I feel like I weigh 265. So the difference between these two forces has to be 265. Because I feel like I weigh that much, and weight acts down, it's negative 265. Now, that is part of the problem so far. What are we trying to figure out in this problem, though? What are we trying to figure out? The density of the object itself, right? The density of the object itself. So, if I wanted to do that, I could go over to here, and I'm going to leave a little room on the bottom because we're going to continue down here. I'm going to continue down here in a moment. Let's work up here for a minute. If I wanted to find the density of the object, I could start with the fact that I know this is true. Okay, the weight of an object is mg. But what is m equal to, really? From the last problem, what is m equal to? What can mass be replaced with? Look at the last problem, guys. Come on. What can mass be replaced with? Very good. Density times volume. I know that the actual weight literally is 315. So that part I can plug in for. So far, so good. The actual weight is 315. That comes from right here. The actual weight being 315. We're trying to find the density of the object, so we don't know that value. We know gravity is 9.81, so I can plug in for that. So can I solve for the density of the object right now? Why not? Why is Ernest saying, no, I can't solve for the density of the object? What's the problem here, obviously? Yeah, two missing variables. You need VO, right? You need VO. What's VO stand for? Volume of the object. When it's fully submerged, what do you know about VO?
It's 0.
Not 0. When it's fully submerged. VO, the volume of the object. It's what? That's not the volume. We're asking about the volume. VO.
Well, it's not like 3/4 of it, it goes before it's the whole thing.
Okay, part of it's not free or above the water. Agreed.
Isn't it like the difference of volume of water?
Correct, but give me more than that. Like so Lauren is saying the graduated cylinder, right? When you drop it in, is the difference in the water level. She's right by that statement. So what other statement can you make? If it's fully submerged, we wrote this down. We wrote this down in the notes for 12.2. When an object sinks altogether, how much water is it displacing? What's VF equal to when it sinks? This is a graduated cylinder. Whenever an object sinks to the bottom, the amount of fluid that it's taken up, VF? Very good. This is the big statement here. When it's fully submerged, we need to know this. Write this down again if you didn't have it off the top of your head. It's an obvious statement when you think about it. The amount of fluid that's being pushed aside when an object is fully submerged is equal to the volume of that object. It's literally taking up the place of the water. So VO is equal to VF when fully submerged. So really, if I want to continue this problem, take a look please. If I want to solve for rho O right here, I need VO. But to get VO, I need VF. Again, let's go through that process I just did there. If I want the density of the object, I need VO. But if I need VO, theoretically, to get VO, I need VF. Once I have VF, I set that equal to VO, it goes in here, and I get rho O, the density of the object. So, here's your buoyant force, right? We were going to use this, I said. 50 newtons. George told us right in the beginning. 315 is your actual weight. You feel like you weigh 265, so it must be 50 newtons. You don't even need to do this, really. You could have just written down FP as 50 newtons. You don't even need these two lines. Okay? Now, what's the formula for buoyant force? What's the actual formula, Ernest?
Density of fluid times the volume of fluid times gravity.
So in this problem, what we could do is actually just solve for VF. And then take that value, plug it in for VO over here. Why am I allowed to solve for VF? I know the density of the fluid. It's submerged in water. It's given. I know gravity. It's 9.81. It's given. Solve this for VF. The density of water is 1,000. Right? The density of water is 1,000. So take 50 and divide it by the product of 9.81 and 1,000. It's going to be a very, very, very small number. What do you got?
0.0050.
A very small amount of volume is being taken up by this unknown object. Okay, this unknown object. Now, I actually put a box around that. I shouldn't have, because that's not the answer, right? We're not done. Put that box right ahead of time, didn't I? There we go. I now have to take this number and plug it in for VO. Why do I have to do that? Because again, it's fully submerged. So the volume of the fluid that's taken up by this object equals the volume of the object itself. Lauren.
Why couldn't you just put in like the density of water and that?
Over here on the right? Because O stands for object, right? This is for the object. It's an unknown object. We don't know its density. We're trying to find that density. We know that the fluid's density goes into the formula for buoyancy always. So that's where the density of water goes in. Okay, we're trying to solve for rho 0 there. So we've got 315 equals rho 0 times 0.005 times 9.81. And solve for rho 0 now. So take 315 and divide it by the product of these two numbers to give you rho 0. Don't give me an answer yet, but just go ahead and calculate it. But don't give me the answer just yet. From the problem's context alone, the object has sunk to the bottom. What can you tell me about the relative density of this object compared to the water? Compared to the water, this object's density is blank. Is greater. Why? Because it sinks. If you sink, you're more dense than the fluid you're in. So the fluid density is 1,000. This density has got to be greater than 1,000. Okay? Use your common sense and your intuition to help you verify the sanity of your answer. The sanity. Sanity, you know what I mean? If it makes sense. Not like you're insane, but if it makes sense, the sanity of the answer. My teacher used to do what's called the sanity check, he used to always say. My calculus teacher always did it. Like sanity check, because people would come up with an answer that was like, you know, you're trying to determine the rate at which a snail was moving in calculus or something was moving, and it would be like 37,000 miles per hour. And it's like, that's a snail. 37,000 miles per hour? That doesn't even make sense, right? So think about the sanity of your answer. What do you get for rho 0? What do you get for rho 0?
6,422.
Agreed? Kilograms per cubic meter. Cubic meter. Okay, 6,422 kilogram per cubic meter. It's about to appear. Okay, it's delayed. Your play's not working right there. 6,422 kilograms per cubic meter. That's only part A, guys. That's only part A. Part B of this problem said find the density of the oil. Find the density of the oil, it said. So in the oil, we have to start looking at our... Okay, there we go, airplane. Just a sec. What's that again?
Just to go over this, like some prefixes. So FB is buoyancy, FG is gravity, obviously.
Weight. Just call it weight, but yes, gravity. Yeah.
And then the rho, the density of the fluid.
Uh-huh.
And then the rho O is density of the object.
Yep. Yep. O for object, not oil here, okay? Now, in part B, oil is now the fluid. In part B, oil is the fluid. And in part B, we're trying to figure out what is the density of the oil. That's what we're trying to figure out now. Again, same problem really, but now we're trying to find rho F, and instead we have rho O. Yes, Ernest?
So then would you basically, like, you would use that formula and say that the buoyancy is 60 now instead of 50?
I think it's 40 now instead of, right?
Oh, yeah.
315 and 275?
Yeah.
Yeah, so let's talk about Ernest is already jumping to it. We know that what does it say? That the actual weight again is 315, but this person feels like they weigh 275, which means that buoyancy must be 40 acting up. Look at my diagram down here. Again, the actual weight is still 315, but it says that when this object is submerged in oil, it feels like it weighs 275. Well, how do we figure that out? 275 from 315 gives me 40. So the buoyant force is just 40. I don't need a free body I don't need a equation FB minus FG really. Okay, if I could just see that. So I could start by saying that the buoyant force is simply 40. But the definition of buoyant force is density times volume times gravity. We're trying to find the density of the object. We know the volume of the object. That was from the last part. We still have it. We know gravity. Did the bell ring or something? Am I crazy? What is going on out there? Oh, they're just doing something? Okay. So if I want to solve for the density of the actual fluid involved here, I need to think about the product of these two getting divided into 40 now. Now, before I even get an answer, what was the buoyant force earlier? Anybody remember from the first part of this problem? Part A, what was the buoyant force there? What was it? It was 50, right? And now it's 40. So the buoyant force went down, didn't it? So what's going to happen to your density? The fluid's density is also going to go down. Because think about it. Look, earlier this was a 50 here, and we had some number. Now it's a 40 here, and these are the same, aren't they? So this number's got to go down to make that 40. It's mathematically, not even logically, but mathematically.
How come you're using the fluid of the water for the oil?
I'm not.
I mean, the volume.
I'm not. This is the volume of the object, really. Think about it. If it's sunk, what do you know? When an object sinks, VO is equal to VF, isn't it? And earlier, we found out that the volume of the fluid was this, which made VO equal to this. It's the same object still. So VO is still 0.005. This is still the volume of the object, really, because it's fully submerged. The density of the oil will become 815.5. And we knew it had to be less than water. Water was 1,000. So our answer does actually at least make sense. Okay, water's density was 1,000. And we said because the buoyant force went down, the density of the fluid went down also. When it was water, this was a 50 here, and this was 1,000 over here. Okay, a lengthy problem. But again, this kind of a problem is not something that you should be like, oh, I'm not going to have to do this on a test. No, this is like one of the longer math problems you would have on the test. Okay, where I might like even step you nicely through the problem with parts A, B, and C, saying like, you know what, calculate this, draw a free body diagram, do this, and I'll give you the steps along the way. But that length of a problem is not unreasonable by any means. Okay, let's go to the next problem. We've got a good amount to get through, so I want to continue pressing through. This was based on the second part of 12.2 that you were to watch on your own. So I'm hoping that you watched. If you didn't, you're going to feel like you're lost right now. You have 4 tires of a car. They're all inflated to a certain pressure. Each tire has a contact area with the ground of a certain amount. And the question says, determine the weight of the car. Okay, determine the weight of the actual car. So if I think about this for a second, if I think about a car, there are 4 tires really. And those 4 tires themselves all sit on the ground. So each of these tires supports how much of the car's weight? 1/4 of the car's weight. Would everybody agree with that right off the bat? It's like you're standing up, half of your weight goes on each leg. So I could find the amount of force on each tire and then multiply it by 4. So I know that pressure is equal to force over area. I'm given the pressure in the tires. The pressure inside the tires is 3 times 10 to the 5th. If that's the pressure in the tires, that's also the pressure that's exerting on the floor. Okay, because of the fact that the car is in a state of equilibrium. The pressure inside the tire has to equal the pressure pushing back on the outside of the tire, so it's balanced. I know that the area of each tire is 0.045. So I could find the amount of weight acting on one of the tires by solving for F. F is the force acting, or the weight in this case. Give me the value. What would I get there? What do I get? Multiply 3 times the 5th. times 0.045. Ernest?
13,500.
Now that's for one tire. That's how much weight one tire is supporting. So the whole car's weight is that times 4. 54,000? Okay, that's the weight on one tire here. This is the total weight of the car. This is just the definition of pressure used here. Pressure equals force over area. That's all we're doing with this problem. Okay, applying it to a different type of problem. I'm going to press on. Okay, if you have a question, please raise your hand, guys. I'm happy to answer. But just raise your hand and I'll stop and answer. But until I see the hands, I'm going to keep going. Yeah. I took the answer of 13,500 times 4 because there's 4 tires for a car. Each tire is supporting 13,500, so the total car is 54,000. A pipe contains water, and the water is at a certain pressure. If you patch a hole with a radius of 3 millimeters with a piece of bubble gum, how much force must the gum withstand? Ever seen these in the movies when a boat springs a leak? They start trying to patch the hole with like gum or like use whatever they can do to patch the hole. Well, the hole has pressure pushing inward. So the gum that you would patch the pipe with would have to have a certain allowable strength to hold it. If not, what would happen to the gum? It would like blow a bubble almost, right? The water would start to make a bubble from the gum, and it would probably explode. The water would come out that hole. So we know in this case that there's a certain internal pressure. So let's start by listing that value. That's the pressure of the water in the pipe. We know the hole has a radius of 3 millimeters, which is 0.003 meters. And the question is, how much force can the gum withstand, or should the gum be able to withstand? So in this problem here, we're really taking a look at the fact that, you know what? We don't have the area, but we have the pressure and the force, right? We've got the pressure and the force, but no areas in this problem. So what should we probably do? Exactly. So what should we do? Pi r squared. Okay, let's write down the area. Okay, let's jot down the area here. I can get a number tomorrow. You're coming to the second, remind me again, first period for the other class? Okay, so we're only going to do a lab in the second period here, which is on the computer, so you can make it up whether they're on that or not during that period. Caroline, one thing, sorry. Just do me a favor, just hand out laptops right now so we can get them ready. Guys, Caroline's going to bring a laptop around. Turn it on, but please don't get distracted. I want to keep doing this while you're doing that. And as soon as we're done, I'll have you guys get started. Yeah, but I want to get to at least another 1 or 2 of these problems before I go any further. What does that area become? So it's going to be a very, very small number.
We got 2.827.
Times 10 to the what? Negative fifth? Is that right? You got negative 6? Yeah, 1 between 2 for most part. Well, let's see. 1, 2, 3, 4, 5, 6, 7. Actually, no. Everybody can get their own. Yeah. Today, everybody can do their own for sure because there's enough. Thank you, Karen. If others can just verify that. I didn't even calculate the area when I did this problem. I just kind of put it in the denominator of the problem. Pi times 0.03 squared? Yeah? Okay. Now, the formula we know is that pressure is equal to force over area. We're trying to find the allowable force of the gum, or the necessary force, we should say, of the gum. So it's just the pressure involved times the area. Hey, this finished? This is actually completed? That's amazing, because look how much filament is left. You see? I thought we were going to run out. There's 1 strand of filament left. That's why I put that next to it. Thinking we'd have to continue, but it actually finished.
Oh, yeah, that's fine.
Awesome. That's perfect. What do I get for the force acting on the gum here? How much force would it need to withstand? All right, for the sake of time, I'm going to write it 11.3 newtons. 11.3? Okay. This is the amount of force the gun would have to physically withstand in order for it to not spring a leak. Okay, in order for the pipe not to shoot water out of that hole. George. How about wait maybe another minute or two? Let me do the problem, and then once we start the lab, let me know. Okay. Here's what I'm going to do at this point. All right, so in this example, we're going to this concept of a hydraulic press. This was one of the topics that you needed to watch the video on because we ran out of time with going over this lesson. So you were supposed to watch the video on your own for this. So I surely hope that you did do that. What you'll notice here is that these two locations are very different. One end of the press is a very small channel where a force is applied, while the other end of the press has a large opening where the force is applied upward. Now, recall please from your notes and from listening to the video on your own time that this is a fluid inside of here. This is a closed container. So if I'm to push down on this, the fluid cannot just leak out the side. So the fluid, when I push down, I literally take this, it's called a piston. This piston is pushed down, and as a result, it pushes the fluid this way, which forces the fluid this way, which pushes up on this object, and as a result, it lifts the object. Hence, hydraulic lift. Hydraulic meaning we're looking at like hydrostatic pressure of fluid, and a lift because it's literally lifting it up. So if you've gone to the mechanic before and they say, we're going to put the car up on the lift. The lift is the item that lifts it up. Well, they have a machine, it's an actuator, where they could actually press up or down, and using hydraulic pressure, it's able to lift or lower that actual car itself. Well, the idea here is that you're getting a mechanical advantage. You can put in a very little amount of force and be able to lift up 500 newtons with this. Okay, that's the whole idea. It's like a lever, or a ramp, or a pulley. All the simple machines that we've talked about, simple machines yield mechanical advantages. That's why with a torque wrench, you want the wrench to be really long because you get a lot of leverage on that wrench. If the wrench is really short, you don't get much leverage there. It's a mechanical advantage based on the length of the lever. Here, the mechanical advantage is based on the cross-sectional area of where the pistons lie. So you'll see here that this is a very small cross-sectional area. This is a very large cross-sectional area. These pistons are actually cylinders. So imagine, okay, here's the piston itself. Now the actual piston either goes up or it gets forced downward. And it's in like a cavity. And that cavity, if any of you have ever seen a car engine work, you see the pistons firing. And you look like a V8 has 8 pistons, a V6 cylinders, pistons. A V6 has 6, and you literally see these cylindrical things moving up and down because of combustion that occurs. That's how a piston moves up and down. Well, in this case, it's similar in nature, but you yourself are forcing down. Something is pushing down on one piston, which raises the other one up. In a car, it's an explosion. It's actually a little mini controlled explosion that forces a piston up, then another explosion forces this piston, and then this happens over and over, which rotates your axle. That's what actually rotates, causes the engine to rotate, which can then rotate your axle itself. Okay, so when we're looking at this example, it's similar in nature to cars and pistons, but we're not looking at something where we have combustion occurring or anything at all. There's a force applied and it lifts something else. Now, because this is a fluid, what I'm highlighting right now, because it's a fluid and because this container is a closed container, we can apply Pascal's principle. And Pascal's principle told us that the pressure inside of a closed container for a fluid is equivalent at any location. Okay, so this is our governing equation that we start with. Pascal's principle says the pressure at one piston equals the pressure at the other piston. Now, what was pressure defined as? What is pressure defined as? P equals what? What do you got, George? Yeah. So this is the force on the first piston over the area of the first piston. And then this is, the force on the second piston over the area of the second piston. Which is the first one? Which is the second one? Which is the first one? Which is the second one? What do you think? I'm not sure I got my shoulder leg. What? It doesn't really matter. Okay, if you want to call this the first piston, that's fine, or call it the second piston, that's fine. As long as the area in that location corresponds with the same thing. For example, let's take a quick look. It says, the piston at location A, well, that's over here at location A. Let's call this area 1 and call this area 2. A or B is the same thing. The piston at location A has a diameter of 5 centimeters. So already on the side, let me list my givens over here. The diameter at location 1 is 5 centimeters, or 0.05 meters. That's, again, the diameter over here. Is it the area? No, it's not the area, it's the diameter. It's the diameter. Next, we're told that the piston at the second location has a diameter of 25 centimeters. Or simply a quarter of a meter. So we've got the diameters of both of these locations. The question says, determine the force needed to lift the object. That's 500 newtons. The object occurs or is located at location 2, so that's the weight that we'd have to lift up at location number 2. So again, we're given D1, D2, and F2. The question is, figure out how much you have to push down with to lift this car up. Now, I talked about the fact that there's a mechanical advantage involved, so you should already recognize that the force needed is going to be something far less than 500. It's got to be. It's got to be. That's why there's a mechanical advantage. So you don't have to push down very hard, and it can lift up a heavy object. That's the whole idea. Okay, it's like a seesaw. We talked about the seesaw with rotational inertia and rotational equilibrium. If you moved out further on the seesaw, you were able to generate more torque. Same thing here. Okay, in this case, a smaller or larger diameter incurs a smaller or larger force. So our goal is just to find F1. Now, do I know what the areas are? The areas given? They're not given directly, right? How could you figure out the areas, Matt? Yeah, exactly. Area of a circle is pi r squared, right? R is really half the diameter. So you can have these numbers if you want first and use the radius instead. Or you can watch what I'm going to do. Make it a little bit easier, I think. So I've got F1 is what I'm looking for. F2 is 500. Now, this is going to be pi times the radius at location 2 squared. The radius, though, is 0.25 over 2. This is the diameter at the second location right here. But to get the radius, I have to cut it in half. So I can literally just write it this way. I could also obviously write 0.125 squared. It's the same thing. Okay? Travis?
Couldn't you also just multiply 0.25 times pi?
0.25 has to... Why could you multiply 0.25 times...
Isn't the diameter times pi the same as the area?
That's circumference. Yeah, you're doing circumference there. Okay. On the left-hand side, it's pi times the diameter, which is 0.05 over 2 squared. Again, why am I dividing the diameter by 2? Because it's really pi r squared. The other formula, by the way, is pi d squared over 4. That's another area formula of the diameter you can use. Okay, pi d squared over 4. See why it's over 4? Because 2 squared here will give you a 4, really. What happens to pi if it's on both sides? Okay, it doesn't matter if it's in the bottom or top. If it's on both sides in the same location, it's got to cancel. So if we're solving for F1, we've got 500 over, this is 0.25 over 2 squared, and times, I'm going to put the other value, 0.05 over 2 squared. Okay, think logically, guys. This is your denominator. How do you get rid of it? Multiply it up on this side, which is what's putting it over here on the far right. Okay, again, we're getting rid of this right here, multiply it up, puts it over here. Take 500 over whatever this is, times whatever this is. For the sake of safety of time, I'm just going to give you the number. The number is going to be 20 newtons. Okay? 20 newtons. So what's the mechanical advantage? Quick, we can do it. What's the mechanical advantage? Think about what mechanical advantage means again. I've referred to this word a couple times. What do you got?
It means that like you don't need as much of a force because there's like a lever or something, or like something that helps you pull up without you doing all the work.
What is the value though? You know the value? You're absolutely right. That's exactly what the mechanical advantage is in this problem. Anybody be able to figure out the value? It's actually pretty easy.
480.
What is it?
Is it? Do you do 500 by itself?
Close. It's not 480, but you're on the right track, Trooper. No. You looked at the change in force. I want to know the change in the, or I want to know the factor of increase or decrease. 25. So you need to take the amount of force that you end up lifting and divide it, not subtract it. Divide it by 20. You get an answer of 25. The mechanical advantage is saying how much you're getting out divided by how much you put in. Okay? Again, write that down if you need to. Mechanical advantage is what you get out over what you put in. For all engineering, all physics, from like this point on, okay, it doesn't matter what you're doing. If it's torque with a lever, if it's if it's a pulley system, if it's a ramp, an inclined plane, any of this stuff, there's always a mechanical advantage involved. That's why you use these mechanisms. So to figure that out, say to yourself, what am I getting from this, and what am I putting in? Divide those two numbers. Okay? The mechanical advantage is a factor of increase. A factor of increase. All right, the next example. How much pressure is felt by an object that's submerged at a distance, or a certain distance of 200 meters in salt water? How much pressure is felt by this object? Now, it's very tempting to start with this. Don't write it down. It's not right. Why isn't this right? I mean, you could use this, but you'd have to do this whole long derivation. Do you know anything about area right now? No. We don't even know anything about force at all. So this is not a very useful formula, even though it does solve for pressure. There's another formula that we learn in this section.
Is the pressure equals the pressure of the atmosphere plus density times gravity times height?
Good. And height in this case is really depth. H stands for the height of the water that's on top of the object. So draw yourself a picture if you need to. Here's our object underneath salt water. It's at a depth of 200 meters. Okay? Literally, this is what's happening. If you have no idea what I'm saying, and you think you've never seen this formula, it means you need to go back to 12.2 and do your homework, which means watch the rest of the video. We never got to this in class. Okay, so if you're like, what is this right now? It means you didn't actually do that work. Please, go home and do that work. P is the overall pressure felt by an object. That's the pressure literally felt by this object. Rho GH is the pressure from the fluid, the water itself. P0 is the pressure from the air on top of the water. So you literally have the air sitting on the water, pushing down on the water on top of the object, pushing down on the object. So technically they're both pushing down on the object, so we sum them together. Okay, this is called the atmospheric pressure, and this is called the gauge pressure. And this is simply the total pressure. How many of you have ever gotten a flat in your car, your parents, or you ever pump up air in a bike tire or a tire? When you measure the pressure inside the tire, use a pressure gauge. It tells you how many pounds per square inch PSI are going into that tire or in the tire. That's actually a measurement of gauge pressure. It's measuring the internal pressure inside of the tire only. It's not taking into account the atmospheric pressure pushing down. Okay, so in this case, all we have to do is plug and chug. P0 is a constant. P0 is the pressure of the atmosphere. It doesn't change. Yeah, I mean, maybe if you're at a higher elevation, there's less pressure on you because you're further up. It means there's less atmosphere above you weighing down on you. If you're lower to the ground, there's more atmosphere pushing down on you. But for the sake of this course, and for the sake of any high school physics course, the assumption is that this is 1 times 10 to the 5. Okay, it's never going to change. It's on your formula sheet at the very bottom. You don't have to memorize this number. Its units are pascals. It's on the bottom of your formula sheet. Now, density. If I didn't know the density, and I'm doing this for homework, how might I find out the density of salt water? Let's say I didn't know the density of salt water, and I was doing this for homework. What might I do? Yeah, Google it, or what's the other thing I said the other day? Look it up where? Yeah, in your textbook. It's in your textbook, okay? Salt water is 1025. Okay? The density of salt water is 1025. And that's units of kilograms per cubic meter. G is 9.81. And we also know that our depth in this problem is 200 meters. Okay? A lot of unit cancellation going on here. We got meters cubed. Those two are going to cancel, leaving behind a meter here. We got seconds squared, kilogram. It's a mess. But you know what? I know that these are all the standard units that we've been using all year. This is a standard density unit, standard acceleration unit, standard distance unit. So as a result, if I'm multiplying these three, it has to have the same units as what I'm going to add to it. So I'm not even worried about what the units are going to be because I know it's in pascals. So the total pressure is 1 times 10 to the 5th plus, I don't even know what that turns out to be, the other part. What does that turn out to be? 1025, 9.81, 200? What's the product of those three numbers there? What's the product of those three numbers? What is it, Kim?
1.962 multiplied by 10 to the power of 5.
Thank you. Agree, disagree? Is he right? Is he wrong? Can somebody else check? You got that? Okay. Then two people all agree with it. That sounds good. So now if I'm adding these two values together, what am I going to get as a result? What am I going to get as a result? Just summing the two together. You didn't get that. I think what she got is right, actually. Sorry, not to mislead you guys, because I got something different. But because the both of you said it, I was going to let it go.
It's 2,011,000.
Check it again. You got 2 million,
At first,
and then you changed it. Check it again. 1025 times 9.81 times 200.
Yeah.
Yeah, 2 million is 11,000.
Like that? 11,050? Okay? So we get this value here, add it to 1 times 10 to the 5th. Hey, you know what? I'm never going to get upset if you give me the wrong number because you're at least doing the work on your calculator. When you're sitting there and doing nothing, that's the stuff that pisses me off, and you guys know that already. Check the answers. I'm glad that the two of you actually checked. Right or wrong, I don't care. I'm glad that you're doing the work at least. Okay, so multiplying those three numbers, you get this, sum it to this. You should get, I got 2.1 times 10 to the 6. Okay, check your number in your calculator. It's scientific notation. I add this and this together, and you're getting this value right here, which is really like 2,100,000. Okay, 2,100,000. That's what 10 to the 6 comes out. So if you look at this, the atmosphere has much less of an effect than the water itself. Okay, if you don't recognize, this number here is really 2 times 10 to the 6. That's what this number is right here. That's really 2 times 10 to the 6. So 2 times 10 to the 6 is much greater than 1 times 10 to the 5. So the water pushing down on you has more of an effect than the atmosphere pushing down on the water itself.
What is PA?
Pascals. Pascals. Okay? It's named after, the guy's name was, I think it's Blaise Pascal, Bliase or Aise, Pascal, French scientist. They named it after him. But Pascal are units of pressure. Okay, what are the pressure units we use in the U.S.? I just said it a little while ago. Yeah, there it is. PSI. Okay, pounds per square inch. What is a Pascal really? Newtons per square meter. Pounds per square inch, newtons per square meter. Same thing really. One's English, one's metric units. There's only a difference. Okay, so that's the pressure felt on an object at that depth. At that depth. All right. Now let's jump right into 12.3, which is what we did in this section yesterday, actually. So this should be a nice, easy review. The lab we do tomorrow is going to be a continuation of 12.3. And we're going to work on those two things in the lab for 12.3. So I think you guys are going to be fine with 12.3, honestly. I think 12.2 is going to be a tough part for this test, just for a little foreshadowing. A 2 centimeter diameter faucet tap fills a 2.7 times 10 to the negative 2 cubic meter container in 28 seconds. What is the speed at which the water leaves the faucet? What is the speed at which the water leaves the faucet? So in these kinds of problems, we need to recognize that we're looking at our continuity equation. The continuity equation tells me, you know what? AV equals AV. But the problem here is that I'm not really given two scenarios. I'm given stuff with time, I'm given stuff with diameter, which is kind of like an area, right? I can make that into an area. But then I'm also given a volume. You see the volume there? How do I know I'm given a volume in this problem? What are the units that tell me it's volume? Meters cubed. Now, please, that V is not volume, that's velocity, right? So we're clearly seeing that this is going to be a little bit tricky. Now, yesterday in class, remember we kind of rushed through the end a little bit when we got to this part? We didn't, slow down and go through it nice and slow. Let me point something out that I didn't get a chance to point out in your section yesterday. If you look at your units for AV, units for A are square meters. Units for V are meters per second. What do those units become when I multiply them? What's meters squared times meters per second? Meters cubed, I heard, per second. So this is, ready? Look at what it is. This is volume. This is time. Volume, time. It's like gallons per minute. If you've ever looked at like the rate at which a tank fills up, or if you pump your gas, it fills up at a rate in certain gallons every minute. After a minute, it might fill up 7 gallons or something. So gallons per minute, meters cubed per second. This is a volumetric flow rate. Jot that word down if you don't have it already written down. I think we wrote it in class though. And this again is really volume over time. So really, a problem like this, we could also just say it equals volume over time. And this is something that's not on your formula sheet. Okay, your formula sheet says A1V1 equals A2V2. That's all it's going to say. But because of the fact that you should know that the continuity equation is relating volumetric flow rates, we could set this equal to volume over time. Now, I'm going to put those little dashes on the top of this V to designate that it's definitely volume. Okay, so if you want to do the same thing, to make sure you see that this is volume, this is velocity. Now, given this problem, we're told that we have a diameter of the faucet. We're told that it fills up, a container with a certain volume at a certain time. And the question says, what's the speed? So if I look carefully, I could just use this part of the formula right here now instead. For your homework last night, you used A1V1 equals A2V2, and they were pretty easy, right? It was plug and chug. Plug in for one, solve for the other. Not that bad. Well, if you're given the volume of the container, you're given the time it takes, you're given the diameter, which in turn gives you the area, you can find the speed or velocity at which it leaves the faucet. Okay, so let's go ahead and plug in what we know. Area is really pi r squared. That's times velocity, and that equals volume over time. So I'm just continuing this formula here. This is like a side note, by the way, if you want to just put a little bracket around here so you show that was just me showing you guys something that you guys in the class. Okay. Now, we don't have the radius. We're given the diameter. What's the radius then? Automatically, if the diameter is 2, the radius is? Come on, everybody. 1. Thank you. 1, please. You should know this. That's like the simplest of geometry possible. Diameter is 2. The radius is 1. It's 1 centimeter. 1 centimeter. So what am I going to put in for the radius? 0.01. Okay, take a look at all of your values now. Again, we plugged in the radius here. We know the volume in cubic meters. We know the time given in seconds. Everything is base units. Cubic meters, seconds, and here is in meters. So I can go ahead and solve for V now. Get rid of pi, get rid of 0.01 squared by moving them all down to the denominator. Take both of these values right here, please, this entire thing, and move it down over here with the 28. That will give us the velocity of this fluid. So take this and move it into the denominator right here. We'll get a velocity in this problem of 3.1 meters per second. It's not that fast of a velocity for water. Okay, 3 meters is from like here, ready? So 3 meters is about 3 big steps. So from the podium to where I am, the water traveled that far in 1 second. It seems like it's a lot because for human speed, that's actually pretty quick. In 1 second to go almost 10 feet is pretty far actually in 1 second. But for water flowing pretty quickly with a lot of pressure behind it, not that fast of an actual velocity. Okay? Your lab tomorrow, your numbers for velocities for the pipe flow are going to be similar to this. Okay? On the order of between like 2 and 7 meters per second. A different approach to a problem that you've seen already in class yesterday and in the homework last night, but we did it differently then. Okay, a little bit of a different approach because we're given volume and time here. So we have to use that secondary part that's circled there. All right, the last one. This one's a little bit more straightforward now. The velocity of a fluid flowing in a pipe at a location A is twice the velocity of the same fluid at location B. No numbers again, right? So it's twice. By what factor does the radius of the pipe change from A to B? So nothing about numbers here, but we have enough information to continue. So the first part says the velocity of a fluid at A is twice the velocity at B. What do I write from that? The velocity at A is twice the velocity at B. Give me an equation I can write from that. Literally, just take what I'm saying, translate it into an equation. Yeah, VA is equal to 2 VB. Okay, VA equals 2 VB. Does that make sense, right? The velocity at A, VA, equals twice 2 the velocity at B, VB. So that's the statement we start with. That's not the equation we're going to use, though, because we know the equation is A1 V1 equals A2 V2. We call the A and B at the top. It doesn't matter. Call this 1 and call this a 2 instead. See what I'm saying? In the problem, I called it location A and location B. You can call that location 1 and call that location 2. It doesn't matter. So for this problem, it looks like it's complicated because we're not given anything else at all. We're literally given nothing else. And the problem says, by what factor does the radius change? By what factor? So we are trying to figure out what is the new radius going to be at that second location. So I need to know what is the radius when the pipe has gotten, or when the pipe is at the second part here. So I'm looking for something that's embedded inside of here. So I can replace area for a circle. These are, by the way, they're all going to be circular pipes. Okay? So you can always assume the area equals what? Half is the pi? Always going to happen, guys. It's always going to happen when pi is in both spots. The last example, pi did not cancel because pi was not in both sides of the equation. Now, we know that the first velocity is twice the second. So what can I do? Bless you. What can I replace this with right here? What can I replace V1 with? By definition, by the first thing we wrote down. V1 is equal to what? 2V2. So I replace that with the 2V2 there. Why is that useful? Why is it useful? Mike?
It's just knocks out a variable.
Yeah, V2 is gone. The fact that we don't know V1 and V2 means nothing. Who cares? Maybe it's 3 and 6. Maybe it's 5 and 10. Maybe it's 1 million and 2 million. All I care about is the fact that it's a proportion of 1 to 2, right? One of the velocities is double the other. So if you go ahead right now and plug in 2 million right here and 1 million right here, you could reduce them and you'd end up getting 2 and 1, right? It's the same thing you're doing by canceling V2. So drop off V2 on both sides. It's gone. And you're simply left with this last part here. we're left with the fact that r1 squared times 2 is r2 squared. What the heck does that mean? Well, we're trying to figure out how does the radius change. So let's find r2. Let's find r2. See what the new radius is. Remember, r1 was the one we started with. How do you solve for r2 here? Jack?
You double R1.
Be careful, not double.
Is that a multiplication symbol or?
No, sorry. So this is a square symbol on the top right. This is squared right here.
Oh my god.
How do I get rid of a square?
You, sorry.
Take your time.
Square, how do you get rid of the square?
How do you get rid of the square? You take the...
You take a square root.
Very good. So take the square root of the left-hand side. Now, it looks a little bit funky, but r1 squared under a square root is just r1. And then what's the square root of 2 is just the square root of 2. So it turns out that the radius of the pipe at the further location needs to be bigger than the radius you started with. By what factor? By what factor?
Square root of 2.
Square root of 2. This is the factor of increase. And that's how much the pipe has to go up by. How do I know this is right? Did I start with more or less velocity? Did I start with more or less velocity? Go back to the problem. This is what I started with. This is what I ended with. Which is more? 2v2 or v2? Yeah, you started with more velocity. You ended with less velocity, right? For the velocity to decrease, the area's got to get bigger. So the radius at the end is bigger than the radius you started with by what factor? Square root 2. Mike, I saw your hand shoot up at some point.
Yeah, no,
Go.
it was
You got it? You sure? Okay. So the idea here is that we're not really given anything to do with numbers at all. And we have to go through this process and say to ourselves, what's happening to that value? Now, let me stop for a minute and ask you a simple question. If this troubled you with no numbers, what should you probably just do? Thank you. Very good. Good job. That's what you have to think about. And this will carry over. If those of you next year that are considering taking like AP Calculus, AP Statistics, AP Physics, any of those kinds of classes, when in doubt, and it's all variables, start to choose numbers. Even for the SAT and those kind of tests. When everything's in terms of variables, one simple technique to solve is choosing numbers for those variables. So maybe call the first radius 1, and then you can solve the second radius. Call the first velocity 3, the second velocity would have been 1.5, half of that. Okay? Does that make sense? All right? That's it for today, guys. So you don't have any actual homework per se.